In the last class, we were discussing about the power spectral density of the random process, and we have shown that the autocorrelation and the power spectral density they form a Fourier transform pair. So this is a well-known theorem which is called as Wiener uh, Einstein theorem. Okay. So if I take the Fourier of autocorrelation, I will get PSD, and if I take the inverse Fourier transform of this, I will get autocorrelation function. And if you find the autocorrelation of the random process at zero lag, you will get as minus 2 plus infinite integral x s of f into dx. Okay. Because for tau is equal to 0, this exponential term will become 1. And this is nothing but the average power of the random process. Okay. Because x as x of f is the power spectral density. So if you integrate the power spectral density, you will get the total power or total average power of the random process. Okay. So to find the total power of the signal, what you need to do is just find autocorrelation and compute autocorrelation at zero lag. That will give you the average power. And from the basic definition of autocorrelation, you can also write Rx of 0 as x of t into x of t, the mean of this. Okay. Otherwise, in general, you have Rx of tau, which is taken as x of t into x of t plus tau, the ensemble of this. So if you put t is equal to tau is equal to 0, you get it as x squared t bar. So it is nothing but the mean square value of the random process. Okay, and we have assumed that if it is stationary, at least White's and stationary, then the mean is not a function of time, and definitely the mean square value will also not be a function of time. So I can simply write it as x squared bar. Okay. So these are some important relationships. So mean square value is same thing as the autocorrelation at zero lag, and autocorrelation at zero lag gives you the average power in the signal. Okay. So you can say that these two are basically same. So the mean square value of the signal that gives you the average power in the signal. Okay. And since your power spectral density is an even function, okay, you can write this average power as the mean square value of the random process, and that is same as the integral of s6 of f df, and it can be written as 2 times integral of 0 to infinity s6 of f into d. Okay, and remember that this mean square value that I'm taking here, it is not the mean square value of the sample function. Okay, means you have a random process, and this is not the mean square value of one of the samples. So you are taking a random variable at t, so you get some samples. This represents the mean square value of these samples, okay, not the mean square value of the sample function, because since the process is White's and stationary, so this is independent of time. So whether you compute at this point or this point, it is same. Okay. So we'll take some examples. Suppose you have a power spectral density which is given like this. And this is B and this is minus B. The total bandwidth is 2B and it is n by 2. So this is the power spectral density of a low pass uh, random process with the white noise. Okay. So generally when you define the white noise has a power spectral density which is constant from -2 to plus infinity. It means the power contribution of all the frequencies is equal, and we take it as n naught by 2. Okay. So because you have the contribution from both positive and the negative frequencies in this case. So that is why this notation n naught divided by 2 is used. So this is a white noise process or a white noise, but the power spectrum, the constant power spectral density, that is n by 2, but the bandwidth is limited. It's a low pass random process. Okay. The bandwidth of this is B, not 2B, sorry. The bandwidth is B because we take the bandwidth only from 0 to the maximum frequency. The negative frequencies by default they are there for an ideal field. Okay. So if you want to find its autocorrelation function, what you need to do is simply find the inverse Fourier transform of this. Okay. As x of f e raised to power j 2 pi f tau into df. And we have already computed uh, the Fourier transform or the inverse Fourier transform of the rectangular pulse so many times, and you know that it comes out to be a sinc pulse. So directly write it, it will become NB into sinc of 2 pi beta. Okay. And if you plot the sinc pulse, it will look something like this. This is the autocorrelation of this. Okay, which is nothing but simply the inverse Fourier transform of this rectangular pulse that comes out to be sinc pulse. And if you compute these zero crossing points, it becomes 1 by 2b, then 2 by 2b, and so on, 3 by 2b, and so on. So this is what is the autocorrelation function for this pulse. And if I suppose say that if I take a white noise in which the power spectral density is constant from minus to plus infinity, and if you find the autocorrelation of this, the autocorrelation function for this will be a impulse signal. Okay. The autocorrelation for this is going to be impulse because the Fourier transform of impulse is constant. Okay, these two they form a Fourier transform pair. So if this is the inverse Fourier transform of this spectrum, then definitely the Fourier transform of this autocorrelation function will be this, right? And how you interpret it? See, if the autocorrelation of the white noise is just an impulse, it means for tau is equal to 0, you will have some correlation, of course, because you are not plotting any lag. Okay, and if you take any two samples of the random process, their correlation will become 0. Okay, so it is highly random in nature. No two samples of the random process, they are correlated with each other. Okay, and for this case, if I now try to find the power of the signal, power of the random process, that can be taken as mean square value, or you can take it as autocorrelation as 0 lag. So autocorrelation function is this. If you put tau is equal to 0, so sinc pulse at tau is equal to 0 will be 1. So what you get is NB. This is the power. Or even you can find the power from this through integration from this. Your Px will be 2 times integration of 0 to b xf of f into df, and that is also NB. Okay. Or you can simply say that the powers average power is basically the area under this curve because you're integrating it, okay, from minus b to b. So this total width is 2b and this is n by 2. So it is a rectangle, okay. So you just multiply 2b with n by 2, here 2 and 2 get cancelled, we get and this. Okay. This is how you can find the power, and the autocorrelation is the power spectral density is given and the average power by taking autocorrelation at 0 lag. Okay. You can take one more example. Suppose we have a random process x of t, which is a cos of omega ct plus theta, and this capital theta is a random variable that is uniformly distributed between 0 and 2 pi. So this example I have taken earlier also. So it has a uniform PDF. This is the theta of theta and this is theta. So you have to find average power of the random process. Okay. So you already know from this, from the deterministic signals, we have seen that if I take a cos of omega ct plus theta, then the power of this is a square by 2. This already we have computed in the course on signals and systems. Okay. But in this case, I don't have a sample function, but rather I have x is a random process. It means for different value of theta, which will lie between, it can lie anywhere between 0 and 2 pi, you will have a ensemble. So one wave, another wave will be like this, then another wave may be like this, and so on. Okay. So frequency and amplitude you are keeping constant, then you are changing the phase, you get different sinusoidal signals. This is the random process. And we are finding the autocorrelation of this random process, or x of tau, that we have done in the earlier class. When we discuss the stationary process, it comes out to be a square by 2 into cos of omega c tau. So it is only a function of the lag, that is the time interval between the two random variables, t1 and t2. So this difference is tau. So if I know the autocorrelation of this random process, then I can find its power spectral density, which is the Fourier transform of this. And if you find the Fourier transform of this, you will get a square by 2. So for cosine waveform, its Fourier transform, in the Fourier domain you have two impulses, one at delta f plus fc and delta f minus fc. Okay, so at f minus fc and f plus fc, this is your delta f minus fc, and you have delta f plus fc, and the magnitude of these is 1 by 2. This is what is the Fourier transform of omega theta. Okay. So when you take the Fourier transform of this, so a square by 2, that is a constant, and for this you will get two impulses located at f plus fc and f minus fc divided by 2, and that will make it as 4. So this is the power spectral density, and the total power, average power, that is the mean square value, which I can take as the autocorrelation at 0 lag. So if you have the autocorrelation function, you put tau is equal to 0, you get the mean square value as a square by 2. Okay. So this is the same thing that you can do when you don't assume that it is a random process, but it is a deterministic signal. So from this you have also the power as a square by 2. Okay. Likewise, you can take many more examples. Like if you suppose take phi of t, which is a DSP-SC signal, double sideband suppressed carrier signal, So it is mt into cos of omega ct plus theta. So we mt is a random process, okay? And theta is a random variable that is distributed between 0 and 2 pi. So you have to find the autocorrelation and the power spectral density of this double sideband stress carrier signal. Okay. So then you can again find r phi of tau, which is equal to mt into cos of omega ct plus theta multiplied with mt plus tau cos omega c t plus tau plus theta, and the mean value of this. This is what is the autocorrelation. Okay. So I'm using the definition x of t into x of t plus tau, the ensemble of this. Okay, expected value of this. And instead of x, I have here phi t. So phi t is attached to this. And this mt is a white stationary process, and it is in general, it is independent of this phi or theta. So I can write it as mt into m of t plus tau, and inside you will have cos of omega ct plus theta multiplied with cos omega c of t plus tau plus theta. Okay, because if you assume that mt and this theta they are independent, then for independent random variables you can separate these two. Okay, now this will become, this is the autocorrelation of the random process mt at tau. So I represent it as both rm times tau, and if you find the expected value of this, you can divide it with 2 and multiply with 2, you'll get 1 by 2. So 2 i's of cos a cos b, can write it as cos a plus b plus cos a minus b. So when you subtract this from this angle, your omega ct plus theta will get cancelled out. What you get here is cos of omega c into tau. And the second term, when you add it, it will become a function of theta. Okay, and since theta is a random variable between 0 and 2 pi, the integration of that will become 0. Okay, that already we have discussed in the earlier classes also. So this is the autocorrelation of your DSB-SC signal. Okay, accordingly you can find its power spectral density. It is the same thing. So here S phi of f will be 1 by 2, and the autocorrelation, if you find the Fourier transform of now this is the autocorrelation function of mt, and if you find its Fourier transform, it will become xm of f. That is the power spectral density of mt. Okay, so this is giving you the power spectral density of phi t, which is the DSB-SC signal, and this SMF will give you the power spectral density of mt, because Rm tau is the autocorrelation of mt. So its Fourier transform will give its power spectral density, and when you multiply this with cos omega c tau, definitely this spectrum will get shifted to plus mc and minus mc. Okay, so this is the basic property of the Fourier transform, and in this you also get 1 by 2, so that 1 by 2 and 2 is again 1 by 4. So this is the power spectral density of DSB-SC signal, and then you can find the, what you can say, the average power. Okay, so phi square t bar, which is the mean square value, that will be r phi of 0 and R phi of 0, R phi of tau is this. If you take R phi of 0, it becomes 1 by 2 Rm of 0 into cos of 0, it is 1. So it becomes 1 by 2. This is the average power or the mean square value of MT. Okay. So we have seen that the power of the DSP signal is half of the power of the modulating signal. Okay, this already also we have shown when we have discussed the modulation. Okay, so this is how the power spectral density and autocorrelation function, they are two important parameters in fact. So the last part we will discuss about the noise analysis, the effect of the noise on the performance of communication systems. If you take a general communication system model, you have a message signal which is the input and that is given to a transmitter. The output of the transmitter is fed to the channel, and in the channel we also have the noise which we call as the channel noise, and the output of this we have the receiver, and this is your received signal. Okay, so this is the general model of any communication system. Here message signal, we have transmitter, that transmitted signal goes to the channel. In the channel, this channel itself can attenuate or distort the signal, and apart from that channel distortion, you also have a noise which gets added to the channel. So at the receiver, we have to basically filter out that noise, and you have to also compensate for any distortions that has occurred due to this channel, and your received signal should be as much same as the transmitted signal, the message signal. Yeah. Okay. Now, if you say in the baseband systems, in the baseband communication or in the baseband analog systems, what you don't have any modulation. Okay, so you directly transmit the signal over the channel, like over a cable or a twisted wires, pair of twisted wires or coaxial cables. So we don't use any modulation in that case. So in that case, what is basically my transmitter and what is my receiver is simply depending upon the bandwidth of this message signal. Suppose message signal has a bandwidth of B hertz. So what I need as a transmitter is simply an ideal low pass filter with a bandwidth of B hertz. Okay, and if you assume that the channel is distortionless, otherwise this channel is also modeled as a system, and if you model this channel as a system, then the output of this channel can be taken as the input to the channel convolved with the impulse response from the channel. Okay, if you model it as a linear and time invariant system. But for the time being, we assume that the channel is distortionless, which means whatever signal we are passing to the channel, there is no effect on its amplitude and phase. Okay, it is basically all pass filter, but all pass filter is not always a distortionless system. All pass means it is passing all the frequencies without any attenuation. Okay, in the distortionless you have two cases, you have two conditions that we have discussed earlier, that your phase response should be a linear function of frequency and your magnitude response should be constant. Okay, because you have to see the effect of noise, not that has been added to the channel, not the effect of the channel itself. Okay, so this is a distortionless system. So ideally I have here a filter with a bandwidth of B hertz ideal filter, and then I'm passing it through the channel. So at the receiver, I have signal plus noise. Okay, now some noise has been added to the channel, and at the receiver, in this case, your receiver is simply a filter because you don't have any demodulator here because you are not doing any modulation. Okay, a message signal with a bandwidth of B hertz, you are passing it through a low pass filter, ideal low pass filter with a cutoff frequency of B hertz. So this frequency band of B hertz is as it is passed. The channel is distortionless, but some noise is getting added to this channel N of T, and when you pass this signal, the received signal, through this receiver, which is simply again a band pass filter with a bandwidth of B hertz. So the output, you will get a signal and signal part S naught of T and a noise term. The signal part will be coming from your empty, okay, and the noise part as output will be coming from the channel noise. So if depending upon the spectrum of the noise, okay, so if I suppose say that my noise is white noise like this is the spectrum of your XNF, I say, noise spectrum, and it gets added to the signal. So you have message signal, and then here you have a channel noise. The noise spectrum is constant, okay, so the power spectrum stays constant, and this signal is getting corrupted with this noise. So at the receiver, you again have a filter like this. So this will pass the signal, and some portion of the noise will also get passed, which is from minus B to B. Okay, this frequency range of the noise is also getting passed to the receiver. So that is why you are getting signal and noise and the output of receiver. The performance is basically defined by S naught by N naught, where S naught is the signal power and the output of the receiver, and N naught is the noise power. Now the signal power, if you see it as naught in this case, because you have a message signal, you are passing it through ideal low pass filter. It means there is no distortion up to this point. The channel that I am assuming is distortionless. The signal that you get here is also same what you have transmitted, and then some noise is getting added to this. So you have signal plus noise are the output of this. You have MT plus MT, and when you are passing it through a receiver, which is again a ideal low pass filter, you will get the empty part as it is. Apart from that, you will get a noise term, okay, which is filtered between minus B and plus B. So in fact, your S naught is same as S naught will be same as empty. So its signal power, if I say signal power will be 2 times integral of 0 to B SMF dA. Okay, so SMF is the power spectral density of message signal. So integrate it from 0 to B and multiply it to, you get signal power. And the noise, if I assume that it is a constant power spectral density, if I assume it is a white noise, then your N naught will be basically 2 times 0 to B N by 2 into df, and that will become N times B. S naught by N naught, which is a figure of merit, what we call a signal to noise ratio, that will be given by S naught divided by NB. Okay, so this is what is called as signal to noise ratio. And the signal to noise ratio that we have discussed here for the baseband analog communication systems, it basically serves as a reference while comparing the signal to noise ratio with the other modulations like they have DSBSC, AM, and so on. Okay. So typically, for voice signal, you must have a signal to noise ratio of 5 to 10 dB. Okay. That implies that your speech is of good quality. Okay. Similarly, your telephone quality signals, they have a SNR of around 25 to 35 dB. Okay. For television signals, we need SNR of around 45 to 65 dB and so on. Okay.